In this video, we are going to discuss the number e and compounding continuously. Now, the number e is a famous irrational number just like pi. And it is one of the most important numbers in mathematics. It's often called Euler's number after Leonhard Euler. Now, e is, the first couple of digits of e are 2.71828. And again, just like pi, it continues to go on beyond that, but those are just the first couple of digits. Now, how does this number come about? Like with pi, it's the circumference divided by diameter. But with e, we can take a look at it using the compound formula that you learned in the previous Edpuzzle video, and using this formula here. Now, the only thing that's different between this formula and the one that was shared with you last week was the fact that our rate is just going to be 1. And the only thing that's going to change is the number of times that we're going to compound per 1 year. So our time is really just looking at 1 year, okay? Now, if I take these different n values and I plug them in and replace n in my formula, when I plug in 1, I get 2. When I plug in 2, I get 2.25. When I plug in 5, I get 2.4883. When I plug in 10, it's 2.5937. And just to show you what 100 would be, it'd be 2.7048. Now, if I were to continue down this table, and eventually if I could plug in infinity in for n, what's going to happen is it's going to end up equaling e. So that's where e comes from, is by using the compound formula that you were given to in the previous Edpuzzle video, and basically just looking at if we were to increase that number of times that we were to apply the interest rate to the money, for example, eventually it's just going to turn out to be e if we do that over time. So just I want to give you an outline as to where e comes from. Now, on a graphing calculator, e is located in 2 locations. You can see that e is right below the pi symbol on the right-hand side. But it's also located on the left side of a graphing calculator, right below the log button. And actually it's on the LN button, if you notice that on the left-hand side of your calculator. So that's where you can find E. And the most common one that we're going to use if you have a calculator is going to be this bottom one, if you hit second and then the LN button. And we'll talk about what that LN button means. Okay. So now that we know that E exists, and if we were to compound that interest rate so frequently that it would be infinitely many times throughout the year, we say that it's compounding continuously, faster than every millisecond that interest rate gets applied to your money or to population. So we also have another formula that's used for compounding, and so it's this one here, and we call this one the PERT formula, as the A represents the amount. Okay, this is your ending total. P represents your principal. Okay, now principal, what that really means is your starting amount. What do you have at the beginning? Now, E is just a number. Like, there's no value that you're going to plug in for E. It's just a value that's located on your calculator. Is that 2.71282? Okay, so it's just a number. There's nothing you're going to plug in for that. Now, the R, just like in that previous formula, this is your rate of interest. Now, this is entered in as a decimal. Okay, you don't want to plug it in as a percent. And then just like that previous formula, again, T represents the time, and important, in years, okay? Time in years. So again, E is just a number. There's nothing that you're going to actually plug in for that location, okay? Now we're going to take a look at some examples of and applying this new formula here. One of the ways we're going to do that is by taking a look at population, okay? Because it's really hard to take a look at that. So consider the Earth's human population, which is increasing exponentially. If we are given an annual growth rate and want to predict the Earth's population in 10 years, what compounding interval should we use? After all, new babies are not credited to the Earth's account only at the end of every year, every month, or every day. So like every second a baby is born, like that population is continuously changing. And so that's why we want to take a look at population as being compounding continuously, okay? Another way is when exponential growth occurs in nature. We use what amounts to continuous compounding. And continuous compounding is what we get when we let the number of compounding intervals approach infinity, rather than say like semi-annually or monthly or daily, when it's only a specific amount or a one-time kind of application. So if we take a look at this population example, the population of Australia is approximately 25 million with an annual growth rate of 1.4%. Assuming this rate continues, what would be the population, what would it be in 10 years from now? So what I want to do is highlight the fact that this 25 million, that's how much I'm starting with right now. That's my principal, okay? Now, I can just put 25 and then in my answer I can put in millions, just to kind of simplify the values. Now remember, we're going to use the value E, okay, that 2.7182. Now we're going to raise that to our power, our growth rate here of 1.4%, but we're going to turn that into a decimal, so that's going to be 0.14. And we're going to multiply that by our time, which we're looking at 10 years from now, okay? Now, the key piece of this is making sure that that exponent, that multiplication that's happening, gets done as the exponent, and that multiplying by 10 doesn't happen later, because that's going to alter the value. So I encourage you to put parentheses around that exponent. Now, if we calculate this, after typing it into my calculator, I end up with 101.3799 in millions. Okay. Or I guess I could just say millions, right? So how I did this on my calculator, just so you know, is that I did 25, and then I did the second natural log button on the left-hand side, and that's how I got the E, and then it automatically prompted that exponent. And then again, I just typed in my exponent using parentheses, and then lastly, I hit enter. And that's how I got my value. Now here's one that I want you to try on your own. Again, we're looking at population, which then means that you're going to be looking at something that's growing continuously. So then answer the question, what will the population be 5 years from now? Now for this question, you're given 4 different prompts. So again, you're going to use the same principle, the same time, and the same rate. The only thing that's changing is your n value. Are you compounding semi-annually, which would be 2? Are you compounding quarterly, which would be 4? Or monthly, which would be 12? But then this one here, since I'm compounding continuously, I'm going to want to use our new formula. Okay? For all of these 3, I would want to use my previous formula, which is my principal times 1 plus my rate divided by the number of times I'm compounding raised to the compounding times time. Okay, so find those values and just see the difference.